Okay, so I want to take a look at an example. Now, forgive me because this chart is, well, it's crooked. So, I do apologize for that, but let me at least make it a little bigger for you. And expand this so that you can see it. So, see, here's a chart, okay? This is how you would start variance, okay? So, like I said, we can begin to examine variability by looking at the deviation of each score from the mean. That means we would subtract the mean from each score in a distribution to obtain a deviation score. So in this case, here's your score. Here is your mean. You would subtract your score from your mean. Now if I did this, let's just go over here. The x, so the mean, or I'm sorry, the score was 65, and the mean, I'm just going to write mean in here, was 83.63. And let's just say that this PowerPoint that we're looking at is again looking at scores, okay? So the same scores or similar scores to what I previously talked about for showing you the range. So again, you have the score, then you have the mean. You would subtract 65 minus the 83.65. Okay? So note that the first three deviation scores are negative. Okay, well first let me go back. I don't want to confuse you, so let's actually do it. So if you have your score of 65 for a test score, and the mean of those scores was 83.5, you would essentially take, always do equal and then parentheses in Excel in order to do a formula. So 65 minus 83.63. So essentially it's just taking the cell minus this cell, and you get negative 18.63. Okay, bear with me. I know this is a little weird, and I know this is a negative. Now going back. Now if you notice, actually the first three scores are negative, and that's because those scores are smaller than the actual mean. That's essentially what that is. As a measure of variability, the deviation score has a certain appeal, and as these scores will obviously be larger as scores, they become more heterogeneous and farther from the mean. Okay? It is often reasonable, or may seem to be reasonable, to take an average of these values or the mean deviation as an index of dispersion within the sample. Now going into this, there are other calculations that you can do, as you can see down here, but I don't want to go into those. But just to give you an idea, which I'll potentially describe later on as the sum of squares, the mean of squares. But I want to get to standard deviation and where this comes from. So when we start out taking the deviation, it's just this plain format. But unfortunately, there's a limitation to that variance as a descriptive measure because it's calculated using squares of a deviation score. And that's not useful for us when we're trying to decide sample population, remember? Sample variability in terms of squared units. So therefore, we bring it back into context by going back to the original units of measure. And that's when we take the positive square root of the variance, and that's where the standard deviation comes from. And that's denoted by S. So, going back to our lovely upside graph here, here is what we're looking at. This is the one that I wanted to be on. This is the equation for standard deviation. Using the top portion for just a second, let's go back and let's look at this. So here is the deviation of each score. That deviation was taken and it was squared. That's where you get the 1044.63. And here's the calculation down here. 1044.63 divided by n, which was 8, because we said we had 8 scores. Here, 8 scores in each group. Minus 1. That's the equation. Okay. So here it is again. And this is where we're coming up for the standard deviation. So now, in this section down here, this is the full formula written out. The standard deviation of a sample or sample data is usually reported along with the mean so that the data is characterized according to both central tendency and variability. So a mean, as we know, can be expressed as this, x with a line over it, and then often you'll see the plus or minus. In this case, it would be 12.21, or if you round it up a bit, 12.22. Because the actual number, it comes out to like 12.21225 or something of that sort. So it's just rounded up. So you would take the mean, which is 83.63, and say plus or minus the standard deviation of 12.12. This tells us that the average of the deviations on either side of the mean, so the average deviation of 83.63, either side, is 12.22. And we can use an error bar graph that shows the values for both groups. And that's this below. So the standard deviation is and can be used a basis for comparing samples. In this error bar graph, it's essentially showing that the mean and error is indicating one standard deviation above and below the mean. The error bars indicate that group A is less variable than group B, even though they have the same mean. Okay, so that is where standard deviation comes from. It's looking at variance, and it starts from taking the deviation of the score, but it's not a feasible number to work with or to compare samples, so we turn that into what we call the standard deviation, which you will see a lot of. And as I've repeated multiple times, generally the standard deviation and mean are reported together. So when you see a mean of just using the same example, 83.63 plus or minus a number, which in this case was 12.22, that's the mean and the standard deviation being reported. I will give you again some word problems and examples of this because I want you to also learn how to use the chart that goes with it. So be prepared to see that coming. But hopefully this at least helps you conceptualize what is the standard deviation, what it looks like, and why we use it. We have to compare data or samples. and this helps us do that. Okay, so I'm going to talk a little bit about t-test, and this is just a very simple breakdown of it. There's so many different type of t-tests, and there's so many different type of statistical tests in general, that in this case it would probably be easier to use them in or some type of worksheet or work problem. But I do want you to understand when to use what statistical test, because if nothing, even if you don't remember the equations or you don't remember how to compute the actual statistical test, whether by hand or using Excel, at least you know when you're reading a research article, if they say they use a t-test, hopefully, and it should make sense why they use a t-test, and if they use the t-test appropriately, was it the correct test to use? Because that's going to help you understand if that article is good. If the article makes sense, and if the what happened or what was done, was the procedure correct, was the treatment not effective or effective, what were the p, all of that sort. A lot of that's going to be because of what did they do statistically to get to their result or get to their answer. And if the statistical tests don't make sense, then their result, their answer, or their interpretation of what happened probably won't make sense either. So the t-test is a parametric test, and it estimates population parameters. It does require assumptions made of variance to be normal and homogeneous, so alike, and it looks at the mean of one or two normally distributed populations. This is a small breakdown. Like I said, there are different kinds out there, so it'd probably just be easy to throw some examples to you using actual problems. But here is a small chart of a type of t-test, the purpose, and then example of when you would use it. Now, the paired t-test is something you're probably going to see fairly often. So in this case, it talks about the purpose, which is the purpose of a paired t-test is to look at whether the mean of the differences between dependent or paired observations is equal to a target value. And an example of that, not OT related, but just a basic example. If you measure the weight of a male college student before and after each subject takes a weight loss pill, is the mean weight loss significant enough to conclude that the pill works? We want to compare those populations. So in this case, you would use a paired t-test. Okay? That's all I have right now. The rest I'm going to put to you in some word problems and worksheets, as I've said a few times now. If some of this still isn't making sense, by all means, just make sure you email me. You're not, again, going to grasp this overnight, but the more we look at it, the more we kind of apply it, the more you see it in articles, the more familiar you will become with it. And again, the goal is not to be statisticians. The goal is for you to take a research article and make sense of it without bypassing all of the statistical information, which is a huge bulk of what's going on in the article, and to really be able to come to a clinical judgment of whether or not you would agree with the treatment or therapy, the results, and then take that information and apply it to your own practice and decide if you're also going to use the same treatment or you're also going to use the same therapy. Or even if you don't, think about, well, what would you have done differently, or what should have been done differently, and that sort. So as always, email me, message me with any questions. I will continue to do these recaps throughout the weeks, depending on your muddiest points and your questions. So hopefully this provided a little more clarification. Again, I know a lot of it may be hazy. It's still new for those that have had some statistics. It may be, you just haven't seen it in a while. So let me know, and hopefully this helps. Welcome to the next week.